Welcome to the first module of the course titled Advanced Statistics and Econometrics. This module is designed to equip you with advanced statistical methods that form the foundation for modern econometric techniques. As we dive into these concepts, it is important to remember that statistics is the backbone of empirical analysis in economics, finance, and the social sciences. Advanced statistics is not merely about calculating means and standard deviations. It involves modeling uncertainty, testing hypotheses, drawing inferences, and using data to make sound predictions. In this module, we shall explore probability distributions, sampling theory, estimation techniques, hypothesis testing, regression diagnostics, multivariate analysis. Let's begin with the foundations of probability and distribution theory. Lecture 2, Probability Distributions and Random Variables. Probability distributions describe how the values of a random variable are distributed. These are divided into discrete and continuous distributions. Discrete distributions. 1. Binomial distribution. O models the number of successes in a fixed number of independent Bernoulli trials. O parameters, NNN, number of trials, PPP, probability of success. 2. Poisson distribution. O models the number of occurrences of an event in a fixed interval of time or space. O parameter, lambda/lambda, rate of occurrence. Continuous distributions. 1. Normal distribution. O bell-shaped, symmetric. O characterized by mean mu/mu and standard deviation sigma/sigma. O basis for many statistical procedures. 2. T-distribution. O similar to the normal distribution but with heavier tails. O used in small sample inference. 3. Chi-square and F-distributions. O arise in testing hypotheses, especially in analysis of variance, ANOVA, and regression diagnostics. Understanding these distributions is crucial for hypothesis testing and inference. Lecture 3, Sampling Theory and the Central Limit Theorem. Sampling theory enables us to make inferences about populations using a subset called a sample. Key concept. Sampling distribution, probability distribution of a statistic, e.g., sample mean. Central Limit Theorem, CLT for large samples, the sampling distribution of the mean is approximately normal, regardless of the population's distribution. Standard error, SE measures the dispersion of the sample mean from the population mean. This underpins the logic of confidence intervals and hypothesis testing. Lecture 4, Estimation Techniques. There are two main types of estimation. Point estimation. Single value estimate of a population parameter. Common estimators, sample mean x/bar x, sample variance S2 S2 S2. Interval estimation. Provides a range within which the parameter lies with a certain confidence level. Example, 95% confidence interval for the mean. Desirable properties of estimators. Unbiasedness, expected value equals the true parameter. Efficiency, minimum variance among unbiased estimators. Consistency, converges to the true value as sample size increases. Lecture 5, Hypothesis Testing. Hypothesis testing is a formal procedure to test assumptions about population parameters. Steps in hypothesis testing. 1. Define null hypothesis H0 H_0 H0 and alternative hypothesis H1 H_1 H1. 2. Choose significance level alpha/alpha, commonly 0.05. 3. Calculate the test statistic. 4. Determine the critical region. 5. Make a decision, reject or fail to reject H0 H_0 H0. Welcome to Module 2. Introduction to Econometrics. Econometrics combines economic theory, mathematical economics, and statistical inference to quantify economic phenomena. Key objectives. Estimation of economic relationships. Testing economic theories. Forecasting future trends. Policy evaluation. The basic model in econometrics is the linear regression model, which we explore in more detail. Lecture 2, the classical linear regression model, CLRM. The CLRM is the workhorse of econometrics. Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus midline horizontal ellipsis plus beta kxk plus epsilon y equals \beta underscore 0 plus \beta underscore 1 x underscore 1 plus \beta underscore 2 x underscore 2 plus \beta underscore kx underscore k plus for epsilon y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus midline horizontal ellipsis plus beta kxk plus epsilon. Assumptions of CLRM, Gauss-Markov assumptions. 1. Linearity in parameters. 2. Random sampling. 3. No perfect multicollinearity. 4. Zero mean of error term. 5. Homoscedasticity. 6. No autocorrelation. 7. Normally distributed errors, for inference. If these assumptions hold, the OLS estimator is blue, best linear unbiased estimator. Lecture 3, Violations of classical assumptions and remedies. In practice, assumptions are often violated. Multicollinearity. High correlation among independent variables. Remedies, drop variable, combine variables, use PCA. Heteroscedasticity. Non-constant error variance. Remedies, use robust standard errors or transform variables. Autocorrelation. Correlation of error terms over time. Common in time series. Remedies, use GLS, Cochrane-Occott procedure. Lecture 4, Time series econometrics. Time series models analyze data collected over time. Key concept. Stationarity, statistical properties remain constant over time. Autoregressive models, they are yt equals yt minus 1 plus epsilon ty underscore t equals \phi y underscore t 1 plus for epsilon underscore tyt equals yt minus 1 plus epsilon t. Moving average models, MA. ARMA and ARIMA models. Test for stationarity. Augmented Dickey-Fuller, ADF. Phillips-Perron, PP, test.